Hi, good evening. Welcome to the live session of the course network analysis. I hope you are able to hear me. So today, this is the last live session of this course. Today is week 12, and since we have completed solving all the assignments, so today we'll be looking at some uh, problems that I have accumulated from various sources. So we'll start. I'll share my screen. I hope you are able to see my screen. Could you just confirm once whether you are
Yes, sir.
able? Okay. So these are some good problems from the whole chapter, more or less. So I have picked up some important, the most important chapters out of the whole subject network analysis, and we'll try to solve. So that includes your KCL, KVL, then Thevenin Norton's theorem, then dependent analysis with dependent circuits, and also lastly the two-port networks. So due to time limitation, I am restricting the content to these chapters only, but you can expect plenty of problems from these chapters in your final exam. So let's start. Murshid Alam, could you please mute yourself? Okay, thank you. So let us look at the first problem. So here they have told that in the circuit given below, determine all the branch currents by nodal analysis. So here this circuit is given, and uh, basically here, or rather, you know let us try to find out what is the, okay, yeah, so yeah, fine. So let us try to determine what are the branch currents, right? So as you understand, branch current basically means, so let us just redraw the circuit once, then we will understand what we need to do, because this circuit can be simplified with the help of source transformation. So if you see that this 100-volt source and this 10 ohm resistor, they are connected in series. So as we saw, that if there is a voltage source and a resistance connected like this, we can easily um, break this into these two components. So this is a current source and this is the resistance, right? So here you see there is a 100-volt source and 10 ohm resistance. So we can apply the same thing here, and we'll try to simplify the circuit. So the circuit would be something like this if we redraw the circuit. So this 10 ohm, sorry, 10 ampere current source is connected from this point to this point, basically from this point to this point. So we can also draw this current source like this only, right? And then we have all of these resistances that are there. Sorry. So this is what the 100 volt divided by 10 ohm is 10 ampere. So this is the 10 ampere source, current source. Then this is your 10 ohm resistor. Again, this is 10 ampere source, and these are the remaining resistances of the circuit. So we can move one step, in fact, two steps further. So this, when you have a circuit something like this, na, so suppose you have this 10 ampere source, then in parallel to that there is a resistance, and again something like this which we have in a circuit. So it can be simplified like this. So if this is I1 R and I2, so this can also be simplified like this. So this would be I1 plus I2, and this would be a resistor R. So this thing we can apply here, provided these two are in the same direction. If this was in the opposite direction, then that this 10 ampere source would have been cancelled by the another 10 ampere source which is pointing downwards. Okay, since this both of these are pointing in the same direction, so we are going to add it. So using that we can now, so let us just, so this 10 ampere source would get added, right? 10 both 10 ampere, and it would become 20 ampere here. And then again you have the resistor, and then the remaining resistances that we have. So this is 10, 24, 10, 10, and here also it's 10. This will be 10 and this will be 20 ampere. Again we will apply a voltage transformation, so source conversion, not voltage transformation, source conversion here. So we will convert this current source into voltage source. So we will just multiply this and then followed by the resistor here. So this 10 ohm resistance is here, and then this is your 200 volt source, right? And then so this is 24, this is 10, this is 10, this is also 10, this is also 10, and this is also 10. So now what we need to do, we will apply simple KVL here, because we are told to find out the branch currents, right? So for finding out that, we need to apply KVL, right? Because here, uh, yeah, so here basically this would be I1, this would be I2. Let me just use a different ink here. So this would be I1, this would be I2, and this would be I3. And by the way, there is a small correction in the circuit. So this, sorry, question. So this would be mesh analysis, not nodal analysis. I'm sorry. This would be mesh analysis in the original question. Okay. So we can also use nodal analysis here, but there would be many nodes, because this would be one node, then this would be another node, this would be another node. In this way, the number of equations will increase. So it's better that we use mesh analysis. So now we will just apply simple KVL here. So what would be the KVL equation in mesh 1? it would be 200 volts equal to, we have this three 10 ohm resistors through which I1 is flowing, 10 plus 10 plus 10 I1, right? Then I2, so I2 would be pointing in the negative direction, because you see through I1 current is I1 through 10 ohm resistance, I1 is flowing from the top to bottom, and I2 is flowing from bottom to top. So similarly for I3, therefore this would be 10 I2 minus 10 I3, right? So this would be 200 equals to 30 I1 minus 10 I2 minus 10 I3. So this would be 20 equals to 3 I1 minus I2 minus I3. So this would be our first equation. Now we need to solve the other two mesh also. Let's put it down here. So this is mesh 2. So here mesh 2, basically this one mesh. So here also there are three resistances, 10 plus 10 plus 10 I2, and then again here also you see both the remaining two currents are in opposite direction to I2, right? So 10 I3 again, and this would be equal to 0 because there is no voltage source here. So 3 I2 is equal to I1 plus I3, right? And finally the third mesh, so this would be mesh 3, and here it would be 10 plus 10 plus 24 I3 minus 10 I2 minus 10 I1, right? So this would be what? 4.4 I3 is I1 plus I2, right? Um, Now what we will do, so basically we have three equations, we now need to solve them carefully. So first we will substitute, so first we will substitute I3 from equation number 2, right, in equation number 3. Okay, so as a result, what so I3 would be what in equation 2, it would be I3 equals to 3 I2 minus I1. So we will just need to put it over here, 3 I2 minus I1 equal to I1 plus I2, right? mm. So this would be what, 13 I2 minus 4.4 I1, 13.2 I2 is equal to I1 plus I2, right? Now just take the things to the respective sides. So this would be 5.4 I1. So so this would be what, 54 by 122 I1, right? So basically if we cancel, simplify, it would be 27 by 61 I1, right? And let us mark this as equation number 4 because we would be requiring this. So this would be equation number 4. Now let's substitute. This kind of problems is a bit lengthy, so you need to do it patiently. So substituting I2 from 4 in equation number 2, right? Put it downwards, we need some space. Just hold on. Yeah. So if we do that, so we are substituting I2 from 4 in equation number 2, right? So if we do that, then it's like 3 I2 equals to I1 plus I3, right? So if we do that, then it would be 3 into 27 by 61 I2 is equal to your I1 plus I3, and this would be I1, sorry. So I1 plus I3. So this is what 81 minus 61 by 61 I1 minus I1 equals to I3. Therefore, I3 is 20 by 61 I1, right? So this is equation number 5. Now what we will do, so just the final substitution. So substitute we will substitute directly in equation number 1 and I3 also from equation 5 in equation number 1. So we will find out I1 in that way. Substitute I4 and other stuff. I2 from 4 in 1 and also I3 from 5 in 1. So if we do that, then your equation directly becomes 20 is equal to, it was 3I1, right? 3I1 minus I2 minus I3, right, directly. So it would be 27 minus 61 I1 minus 20 by 61 I1. So now it would be 20 into 61 is equal to 3 into 61 minus 27 minus 20 I1, right? So I1 would be what, 20 into 60 is your it is 1200 minus 183 minus 47. So if we just calculate it, it comes out to be uh, approximately 8.97 amperes. Once you find out I1, remaining two are very easy. So I2 would be what? I2 would be 27 into 61 into 8.97, right? So it is around 3.97 amperes, and I3 would be 20 by 61 I1, so 20 by 61 into 8.97. So it comes around 2.94. So these are the three required answers. So the main important concept is this source transformation here. I mean, you can also do like this, right? Because you see
Yes,
your
sir.
this, hello.
Yes, sir.
Yeah. So basically, the important thing is that you need to correctly understand the source transformation, right? Because this you can also apply directly the KVL to this circuit, but it would be complex because here you see there is one mesh, there is another mesh, so there would be four mesh, right? And then applying KVL here also would be pretty difficult because this would be I1 I2, then your I1 minus I2 would be 10 amperes, then I mean it would be more complex. So a slightly faster method would be to apply the source transformation, and you can certainly expect this type of questions in your uh, in I mean the final exam that will be appearing for. Maybe the circuit won't be as large as this, but this kind of source transformation would definitely be there. Okay. So fine, let us now move to other the second question. Anyone meeting in the lobby? Yeah. So in the next question, see, this is a super node problem. What is super node? Basically, this is a node here, right? This is a node here, and this is also a node here, right? So in between two nodes, you have a voltage source connected. So in that case, this becomes a super node, right? Because these two nodes are connected by this voltage source. So here, what is mentioned that we need to find out what is the value of V0, right? So this problem is pretty simple provided you know the analysis. Now for finding out the V0, you can apply KVL here. I mean, here there would be two mesh here, but what I would do, I would apply a KCL in order to make you understand the concept of supernode. I mean, we did saw some problems of supernode while we were doing the assignments, but this by doing this problem, if in case you have forgotten the concept, the thing would, I mean, you will again remember it. So let us apply KVL directly to this circuit. So let us say that this is node number 1 and this is node number 2. So I'm sorry, we would be solving it by KCL, not KVL. Okay. So let us say that this current is I, right, through this I mean circuit here. Then this is I1 and this is I2, right? So how is node 1 and node 2 connected? See here, this voltage source of 12 volt, it is pointing from node 1 to node 2, right? So therefore node 2 ka voltage is higher than node 1 by 12 volts. Okay, so this is how the two nodes would be connected. Now we will just simply apply the KCL rule here. I equals to I1 plus I2, and then what is your I1? Sorry, I. It is nothing but V0. This is a dependent voltage source. So V0 by 2 minus V1, right, divided by this 1K resistor is equal to V1 by 2K. And then here, so let us say that so I mean, through this resistance, how much current is flowing? It is I2, right? So we can directly write V2 by 1K, right? Now, your here, if you see this V2 would be equal to V0, right? Because V0 is the voltage applied reference node. So now we can directly solve this. So V2 is equal to V0. So this would be how much? So V0 by 2 by V1 is equal to V1 by 2 plus V0, because V2 is equal to V0. And now this would be, if we take this to the other side, so V0 by 2 is equal to 3V1 by 2, right? So therefore V0 is equal to 3V1. Now we need to find out what is the value of this thing, right? V0. So V1 would be what? It would be minus V0 by 3. So let us call this equation number 1 and let us call this equation number 2. So simply substitute V1 from 2 in 1. So this would be how much? Your V2 or the V0 is minus V0 by 3 plus 12, right? So this would be how much if you take to the other side? V0 plus V0 by 3 is 4 V0 by 3, and this would be 12. So therefore V0 is this gets cancelled, so this is 3, therefore this is 9 volt. So this is your answer. This is where we apply the concept of super node, because see here we didn't get a numerical value of v0, right? We were getting a relation between v0 and v1. However, using the node concept of super node also, we were getting a relationship of v2 and v1, right? So if we use this, we get a value of v0. So this is how you solve this kind of problems. Okay, I hope this is clear.
Yes, sir.
Okay. This kind of problem, so this, as you can see, this is a very small problem, I mean doesn't take much time. So now let us go to the other problem. So this problem is a bit lengthy and we need space for that, so I'll just shift this thing downwards. Just a minute. So here we need to determine the node voltages, right? So let us quickly first mark what are the nodes. So this is node 1, this is node 2, and this is node 3, and let us ground this node. And here also see there are scopes of source transformation, right? Current source to voltage source transformation ka scope is there. So when you see that, because if you don't do that, there would be extra current paths, right? So the number of equations would increase. So it's, while you are applying a nodal analysis, try to convert the current source to voltage source if that's possible. Okay, it would simplify your analysis. So this would be what, 10 volts, right? So I am directly drawing from this 5 ohm source. So this would be what, 10 volts, and this is again 10 volts here. Right. This is our 6 ohm resistances. Sorry, 6 ampere current source here. Sorry for my time. And again here we can also apply a source transformation, right? So let us first draw the voltage source. So this would be plus and this would be minus, because the current source is pointing from node 3 to ground node, right? So therefore this plus would be facing the grounded node here. So this would be how much, 7 volts, and again there would be a resistor here. So this would be your 2 ohm resistance. This is 1, this is 5, this is 6 amperes, this is your 10 volt, this is also 10 volt, and we are left with this 5 ohm source, resistor. So now we can apply nodal analysis. So let me mark this in a different color. So this is node 1, this is node 2, and this is ground node. And now let us apply the KCL rule here. So let us say that this current is I1, this is I2, this is I3, and again let this be divided into I4 and I5, and finally this into I6. Right. Let us follow this convention and proceed. Because see here, you need to apply KCL only. You can't apply KVL, because in the question they have told you to determine what are the node voltages. Means this node, this node. So you can also do that by using mesh analysis, but that would be complex. So safer way would be to use the node analysis. So let us first write the equation of node 1. This would be I1 is equal to I2 plus I3 here, right? So what is I1? It's 6 amperes. What is I2? It is, carefully see, I2 is between 1 and 3. So this would be V1 minus V3 by 5, right? And this is I3 is between 1 and 2. So this is V1. This would be plus 10 minus V2, right? Because there is a voltage source here, and this is 5 volts, 5 ohm, sorry. So this, if you take this to the other side, this would be 30 equals to V1 minus V3 plus V1 plus 10 minus V2, right? So your equation would be 20 is equal to 2V1 minus V2 minus V3. So this would be your node 1 ka equation. Now, before applying nodal analysis to node 2 and node 3, carefully see. So if we see here, I3 is getting divided into I4 and I5, right? So if I write I3 is getting divided into I4 and I5, and this is also a super node ka problem, because node 2 and node 3 are connected by this 10 volt source. There is no resistance in this path, right? By which you can apply the, the voltage drop across the resistance, the current flowing through that, right? There is definitely a current flowing through that, but you can't write using a resistance because there is no resistance. So instead you can do it like this. So what would be the nodal analysis ka equation at node 2? It would be I3 equal to I4 plus I5, and similarly here it would be what? It would be I2 plus I5 equal to I6, right? Because I6 is entering node 3 and leaving node 3, and I2 and I5 is entering node 3, right? So this would be node 2 ka equation. And similarly, what would be node 3 ka equation? It would be I2 plus I5 equal to I6, right? So I2 plus I5 equal to I6, right? So what is common? You see I5, right? Now try to replace that. So you see here one thing is common, right? I5 is common in both the nodes, because the see here, because the I5 is flowing between node 2 and node 3, right? So definitely, therefore this would be the common thing which is connecting both the nodes, right? So try to replace that, and if you do that, your problem will be solved. See, if we replace, so if we write I5 equal to I6 minus I2 and replace this here, what it would be? So I3 is equal to I4 plus I6 minus I2, right? Therefore, take it to the other side. This would be I2 plus I3 equal to I4 plus I6. So see here, what is I2? This is the current flowing through this path, and I3 is between node 1 and 2, and your I4 is from node 2 to ground, and I6 is node 3 to ground. So you see, you have framed the equation which is connecting both node 2 and 3, right? So therefore, let us write this as nodes 2 and 3. So now, um, and also we need one more equation. What is that equation? It is nothing but, see here, it is this supernode ka equation which we saw here. So V3, so this voltage source is pointing towards node 2. Why? Because this plus sign is towards node 2. Therefore, we will write V3 plus 10 equals to V2, right? We saw in the previous problem. So V3 is equal to V2 plus 10. Now we just need to utilize this, and if we do that, we will arrive at the correct answer. So before that, let me just pull it this thing downwards. So let us, what is the KCL now? We will utilize the KCL how these things are related. So what is I2? I2 is nothing but V1 minus V3 by 5, right? So I2 is nothing but V1 minus V3 by 5. And what is I1? Sorry, I3, it is V1 minus V1 plus 10 minus V2 by 5. So V1 plus 10 minus V2 by 5, and this is equal to I4. What is I4? It is nothing but V2 by 1, right? Between node to ground. So V2 by 1, and finally this thing. So this is V3 plus 7 by 2, right? I6 V3 plus 7 by 2. So V3 plus 7 by 2. So these are the equations. Now we need to solve these two. I mean, see here we have this equation,
Sir,
and yeah, hello, yeah,
sir, V3 is equal to 10 minus V2, na?
V3 is
10 minus V2.
no. V3 how will, so you are telling V3 is 10 minus V2? No,
Yes,
how?
sir.
How?
Sir, in previous question,
Hmm.
VT is equals to V1
Yeah,
plus 12.
this question, question
Yes, sir.
number two. Ah,
Yes, sir. Yes, sir.
yeah,
Here, V2 is equals to V1 plus 12.
yes.
Or, sir, next question, confusion, sir.
See, you need to see in this way. So where is the 12 volt source pointing towards? Where is the plus sign pointing towards? Is it towards
Yes, sir.
node 2 or node 1? It is to a node
Yes, sir.
2, right? So
Yes, sir.
therefore, you will say that node 2 ka voltage is, I mean not times, so it would be higher than V1 if you add plus 12 volt to it, right? So that is why it is V2 equals to V1 plus 12, because you are summing. So it is this node, and this node is connected by this 12 volt source, where the voltage node 2 ka voltage would be higher than V1 if
Yes,
you add this 12 volt source, right? You
yes, sir.
understood this, right?
Yes, sir. Hello, sir. Sir, video pause, sir.
Hello. One minute. Yeah, Muksidalam, can you hear me? Hello.
Hello.
Yeah, can you hear me now?
Yes, sir.
Yeah, there was some internet problem from my side. Sorry for that. Right. Yes. Can you see the screen now?
Yes, sir.
Okay. Yeah, so as I was saying, so if you see, so if you have understood the previous problem, you just need to note where the plus sign is pointing towards. So in the
Yes, sir.
previous question, it was pointing towards node 2, right? Now it is from node 1. So now it is pointing from node 3 to node 2, right? So therefore node 2 ka voltage would be higher
Yes, sir.
from node 3. And by how much? So the value is that you need to add 10 volts to node 3 ka voltage. Therefore, your equation would be V2 equal to 10 plus V3,
Yes, sir.
right? So in the previous thing, V2 was higher than V1 by how much? By 12 volts. So therefore, V2 was V1 plus 12. Now here, in the same way, V3 would be 10 plus V. Uh, V2 would be 10 plus V3, right? You need to
Yes, sir.
understand. Yeah. So now is your doubt clear?
Yes, sir.
Okay. Okay. So now, having done that, now we will just simply solve this. So this would be what? V1 minus V3 plus V1 plus 10 minus V2. So and this would be what? So 2V1 minus V2 minus V3 by 10 plus 10 by 5 equal to 2V2 plus V3 plus 7. Now just take this to the other side. 4V1, 2V2, 2V3 plus 20. 10V2, 5V3 plus 35. Right. Yeah, can you hear me now, Mr. Alam? Hello?
Hello. Yes, sir.
Yes, sir.
I.
Okay, okay. Yeah,
Yes.
so there is some problem here on IIT Bombay's network. So I have connected through my hotspot. I hope yeah, you can see my screen properly also, right?
Yes, sir.
Okay, fine. Yeah. So if we just take this to the other side, so this would be 4v1 minus 2, 12v2 minus 7v3, and this would be 15, right? So this is the third equation, right? Because if you remember, we had so this is the second equation, basically the supernode equation. Now we just need to substitute everything here, and this process is very critical, right, in the whole thing. If you do this wrong, you receive 0 marks because your answer is wrong. So substituting. So first, what we'll substitute? We'll substitute V3 from equation number 2 in equation number 1. Okay. So V3 from 2 in 1. So if we do that, This would be what? This would be 20 equal to 2v1 minus v2 minus v2 by 10. So this would be how much? This would be this would be 1 minute. This would be not plus. This would be not minus. This would be plus, right? Because v3 is v2 plus 10, right? Sorry for that. So if we do that, this would be 30 equals to 2v1 minus 2v2. This would be v1 minus v2 equals to 50, right? And let us mark this as the equation number 4. Then just space. These problems are a bit lengthy. Okay, anyways, so let's just first finish the problem. So now again let us substitute this v3 in equation number 3 here, right? From equation 2 to equation 3 here. Again I'll just copy paste this one here. So now just substituting in equation number 3, right? So this would be what? 4v1 minus 12v2 minus 7. This would be how much? Your yeah, this I have written wrong. Yeah, you are right. This would be v2 equals to, yes, yes. I told right, but I wrote wrong. Sorry for that. Yeah, so this would be v2 equals to uh, v2 equals to v3 plus 10, right? So v3 would be v2 minus 10. Yes. Yeah. So therefore this would also be minus here, and this would therefore become 10, and this would become 5, right? So okay, so this would be v2 minus 10 is equal to 15, and again, so let us just solve this. 4v1 minus 12v2 minus 7v2 plus 70 equals to 15. So if we just simplify everything, this would become v2 equals to minus 55, right? So now what? So see here we have got equation 4 and equation number 5. So what we will do? We will just simply.
Sir.
Hello.
Hello, sir. The value
Yeah.
of V3 is equal to V2 minus 10.
V3 equals to V2 minus 10. Yeah.
Okay.
Yeah. Yeah. See na. I told you na. So see again.
Yes,
See I
yes,
mean again it's. So V2, this voltage source is pointing towards V2, right? So voltage to, I mean node 2 ka voltage would be higher than node 3 voltage, right? So this would be
yes, sir.
V3 plus 10, right? I did a mistake.
Yes,
By mistake I wrote this as plus. Yeah. So this would be what? Okay. So let us just eliminate what you say V1 here. So we will just multiply equation 4 in with 4, and then subtract it directly from 5, right? Because you see the it also has a coefficient of 4 v1 here in equation number 5. So this makes the process simpler. So V1, 4V1 minus 4V2 minus 4V1 plus is equal to 19V2, and this would be how much? This would be 5 into 4, right, plus 55, right, because this is minus, this would be into 1. So this thing will get cancelled. So this would be 15V2 is equal to this would be 20 plus 55, and this would be 75, right? So therefore V2 would be 5 volts. Once you get that, your this thing becomes very simple. So V1 would be what? V1 would be, if we substitute in this equation, this would be what is equal to 5. So V1 would be 10 volts. And you also know what is V3 equation, right? So V3 is 10 minus V2. Very simple. So V3 is 10 minus V2, and this is 5 volts. So these are the three node voltages that the question has told you to determine. Right? So in the question, if you see, they have told you to determine the node voltages. And see, the main concept, see, this analysis is simple, but here the important thing is the source transformation. If you would have applied nodal analysis directly to this circuit, it would have taken much longer time for you to analyze, because here there would have been what, one, two, three, four, five, six, seven equations, right? Instead, we have three equations, and that is the power of this source transformation. And always remember the principle of super node. You need to just see where this plus sign is pointing. If you see it is pointing towards one particular node, the voltage of that node would be higher than the other node by how much. So you need to just add the magnitude of this voltage source. That's it. So that's the principle. Okay. I hope you have understood this. This was a pretty lengthy problem, and the problem is pretty lengthy, but you also need to apply the concepts. Okay. I hope this problem is now clear.
Yes.
Okay. So now we will now move to the Thevenin and Norton's problem. Before that, I need to clear the space because these problems are taking a lot of space. See, after nodal analysis, Thevenin-Norton superposition theorem, these are the two most important concepts of network analysis, and you will, I mean, you will get a lot of questions on this. I mean, be sure of that. Okay, fine. Uh, Now, so see here, we will now move to the Thevenin and Norton equivalent. So we will also see some dependent source ka problem here also, and we will see how to deal with them. So it's just a revision for you. I have told you the concepts previously also, right? So here they have told you to find out the Thevenin and Norton equivalent circuits here. So again, see, there is a scope of, you know, applying this superposition principle here, right? Because you see, you have a current source and a resistance connected in parallel similarly here also, right? And when you are given this kind of thing now, that you need to apply Thevenin and Norton's theorem, there is a shortcut to it. So you don't need to, apply Norton's theorem separately and Thevenin's theorem separately to this circuit. So there is a shortcut. Once you find the Thevenin voltage and the Thevenin equivalent resistance, you can find out the Norton's short circuit current. So we'll come to that, but let us first find out the Thevenin equivalent of the circuit, right? So we will just first simplify this circuit. So this would be how much? There is a resistance. This would become a voltage source here, and this is again a voltage source, right? So this is a voltage source, resistance here, and again this would be pointing downwards because the 3 ohm current source is pointing downwards, right? And this is the, and I mean here there is this terminal VAB, right? And this is how much? This is 5, this is 15 volts, this is 14 volt, this is 14 ohm, this is 6 volts, and this is, sorry, 6 ohm, and this is 6 volts, right? So now, can you tell what would be VAB? So basically VAB means, so we need to find out the Thevenin voltage across this. I just, so here there would be a VTH, right? Because they have told us to find out from A to B, right? So this would be VTH, right? So therefore we can write our VAB would be equal to VTH. So this is the potential across this 5 ohm resistance and also this voltage source, right? So can you tell me, so suppose if I, so this is a simple mesh analysis, right? We need to find out the current using simple KVL rule, but can you tell me what would be the VTH value here using 5 ohm source only? So you don't need to solve the circuit to find out what is the current I, but if I tell you what is tell you to write what is the value of VTH directly looking into the circuit, what would be the value? So what would, how would I write VTH here? Can you tell me if you are still in the meeting, Murshid Alam? Yeah. So
5
what
I
would be
minus
the,
15.
yes, yes, exactly. Yeah. So now though your circuit is done, you just simply apply KVL here. So this would be 6 plus 14 plus 15, right? Because all of this you see, plus is pointing towards minus of this source, and again plus is pointing towards minus. So all of this you can say they are pointing in the same direction, and this is also aiding the current, right? Because from each of the source you see, the current is coming out of the plus terminal and entering into the negative terminal, right? So having done that, now this is pretty simple. So this would be I, right? So this would be how much? See, this would be 1, right? Because 20 plus 35, and this would, no, sorry, not 1. So this would be 25, right? So I would be 7 by 5. Right, so now just simply substitute here. So VTH would be 5 into 7 by 5 minus 15 volts. Right, so this would be minus. VTH is minus 8 volts. Okay, so this is a Thevenin equivalent voltage, and what would be a Thevenin equivalent current? So, sorry, resistance. So, in that case, if you are provided with the ammeter current source, you need to open circuit it and you need to short circuit the voltage source, right? So here we have 3 voltage source, we need to short it, right? So if we do that, then it would become, right? So A B, and this is 5, this is 14, and this is 6. Therefore what would be RTH is, which is also equal to RAB, it is 5 in parallel to 14 plus 6, right? I hope this is understood, right? A very simple circuit. So this is 25, so this would be equal to 4. Bas, that's it. So now your equivalent Thevenin circuit would be how much what. So you have a VTH voltage source connected, and you have in series with that there is the Thevenin resistance, right? So this is the equivalent uh, Thevenin circuit. Now in the problem they have also told us to find a Norton equivalent. Now in Norton, so what is a Norton equivalent? So we can directly derive from the Thevenin circuit. So just see they are interrelated. It is nothing but you have a ISC or IN, right? So let me write like ISC, and this is your RTH. So in Norton equivalent resistance, Norton equivalent circuit, that equivalent resistance or the Norton equivalent resistance is equal to the Thevenin equivalent resistance, right? So, so you, I mean, see here we can apply a source transformation because this is connected in parallel to this. So if I just multiply ISC into RTH, na, this would be nothing but VTH. So just remember this rule here. So, if you just remember this, nothing else is required. So therefore, what would be our ISC or Norton's current? So this would be 8 and this was 4, right? So this will be 2. So ISC is 2 amperes. So therefore, this is your answer, and also the other. I hope this is clear, right? But if you have any doubt, you can ask.
Okay.
Is it understood?
Yes, sir. No doubt,
Okay.
sir.
Okay. Fine. Mm. Uh-huh. So this question got mixed up here. Just a minute. Anyway, so just this thing downwards. Hmm. Okay. So let me just redraw the circuit for this question, and then I will just. Okay, so let me just first write what is the question number 7. I have the question with me, so this is question number 5 is there. Yeah, just a minute. Yeah, so question 7 was find Norton equivalent Rn and current In at the terminals A, B of the circuit. Drag it downward. So when you are trying to solve the problem like this, one thing I could have done is that I could have directly solved and then explained the question to you, but then that would have been, I mean, the way you are understanding now wouldn't have been possible if I would have written the question earlier, right? So let me just draw the circuit of question number 6. Yeah, question number 6, the circuit is something like this. Just give me some time. is 8 ampere. This is terminal AB. This is 10 ohm. This is 20 ohm. This is 40 ohm, and this is 50 ohm. Yeah. Oh, no. Yeah, still now we do have space. Sorry for that. Anyways, now let us focus on this circuit. Let's pull it a bit up. We have more space. Yeah, really sorry for the delay. So in this circuit, as you can see, we need to find out the Norton's equivalent uh, at the terminals AB, right? And this is a dependent source, so that is why I have given this problem. So clearly you can see, for finding out the Norton's equivalent circuit, we need to short this terminal, right? And if we short this 50 kilo ohm will go, right? So that would therefore be something like this. So this would be the equivalent circuit where this is, let's say, ISC, this is FTI1, this is 0.001 VAB, this is 8 kilo ohm, and this is I, and this is 2 volts, right? So therefore directly you can write what would be ISC, it would be minus 80I1, right? Simple. So now you need to apply KVL in this loop. And yeah, also see here, one thing I forgot to tell. So VAB is 0, right? VAB is 0 because you have shorted this. So this is my ground terminal. So you have shorted this. So I need to just change this. So this would be 0, right? I hope you understand this, right? Because we have shorted this terminal, that AB terminal, right? So once we short this, this is so VAB would be 0, and therefore VAB 0 means the voltage source is shorted. So now our analysis becomes very simple. So I would be what, 2 by 8 milliampere. So therefore 1 by 4 milliampere. Therefore ISC would be how much? ISC would be minus 20 sorry, not, yeah, minus 20 milliampere. Yeah. So I hope this is understood, right? Very simple. Quickly you are able to solve, right? You understood, I hope.
Yes, sir. Understood.
Yeah. So now the next thing is that, see, they just didn't told us to find out the Norton's current. We also need to find out the Norton's resistance. But this is a dependent source, so we need to find out what is VTH, or the Thevenin, or the open circuit voltage across AB, right? So we need to find out VAB, right? This needs to be found out, and from there RN or RTH would be equal to VAB by ISC, right? So the problem, the analysis similar to this, similar to the previous question. So once you do that, again we need to redraw the circuit for finding out the Thevenin equivalent voltage across VAB. So this is AB terminal. This is 80I. This is 0.001 VAB. This is 2 volt. This is 8K. And this is I, right? So your VAB would be what? It would be the source transformation only. So 80 80I into 50K, right? So I am not doing anything with the K. So this is your equal to VTH only. I am not making any change to the K, right? So K is nothing but 10 to the power 3. I am not doing anything to that. So this would be 1200. Sorry, 40, right? 4000 I K into I, right? I am not doing anything to that. Let it be like that. It will get cancelled at the end. Uh, okay, so before that we need to shift all of these downwards. Just give me some time. Okay, I hope this much space will be sufficient. Yeah. So now we need to apply this KVL in this loop. So this would be how much? 2 minus 0.001 VAB is nothing but VTH, and this would be equal to 8K I1. So now just substitute this thing here. So this would be what? 0.001 into 4000 K I1. This is 8K. So this minus and this minus is plus. So this is how much? Um, this would be, so this is how much? 1 by 10, 1000, and this is 4000. So this will go. So 1000 will go. So this would be 4K I1 is equal to 8K I1. Right. So this would be what? 4K I1. So I1, sorry, I. So this would be what? 2 by 4 milliampere. This would be 1 by 2. So therefore, now you can directly find out VTH. So VTH would be 4000 into K. I can also write it as 1 by 2K ampere, right? Because milli is on the numerator. So this would be 2K, and this would be this thing. So this would be 2 minus 2 kV, okay? Because this 1000 is there. Just don't get confused by the symbol, okay? So K is 1000. So therefore, what would be RTH? RTH would be VTH by ISC, right? So 2000 divided by, what was ISC? It was minus 20, right? Milliampere. So this is how much? This is 100. So basically 10 to the power 5 sorry, not ampere, resistance, or it is equal to zero point 0.1 mega. So this is, so therefore your equivalent circuit would be something like this. This is your zero point 0.1 mega ohm, and this is your minus 20 million. So basically this would be pointing downwards. This is the solution to the problem number 5. I hope this is clear. If you have any doubt,
Yes, sir.
you please ask. Okay, fine. Again, let me make space for question number 6. So push this down. I hope this much space will do here. Yeah. Okay. So in same thing here also we need to find out what is the Thevenin and Norton equivalent. But here there is a catch. See, we can solve it quickly. So for finding out what is the, so first we'll go with Thevenin equivalent. So we will apply KCL here. So let us say this is I, this is I1, and this is I2. You can apply KVL also, but it will take some time. Okay. So let us say this is I1 plus I2. So what is I? It is 8 amperes. What would be I1? This would be simple current divider rule. So 8 into this total resistance, right? 60 divided by 60 plus 60, right? Quickly. So this would be 4 ampere. Similar, therefore I2 would be 8 minus 4, right? I minus I1 would be 4. So therefore, what would be VAB? So can you tell me what would be VAB, Murshid Alam, or VTH here? Hello,
Yes,
hello.
sir.
Yeah. What would be VTH here in this circuit? So the across these two terminals, you need to find out VAB or VTH. What would be the equivalent circuit? Sorry, equation, not circuit. What would be VTH? How will I write?
VT.
So here across, so this is terminal AB, right? So first, let us say what is. Let us ground this, okay? So what would be VA? You tell me. Forget about VAB. What would be VA? Can you tell me? So this is A, right? This is terminal A, and this is grounded. So what would be VA? The current that is flowing through this path is I, right? So it is flowing through the entire 10 and 50 ohm resistances, and similarly for I2, 20 and 40. So what would be VA?
15 to 10, 15 to I1.
Yes, yes. And what would be VB?
50, sorry, 14 to I2.
Yes. And what would be VAB? How do we write VAB? It is nothing but VA minus VB, because this is the potential difference across this, right? This path. So therefore, this would be 50 I1 minus 40 I2. And once you have this, so I1 and I2 are the same, right? We saw I1 and I2 are 4 amperes, so therefore we can write 10 I1, therefore this is 40 volt. Quickly you can solve this. Okay. So now what would be RTH? See, for RTH, you need to open circuit this, and therefore your equivalent resistance it would become something like this. So if I draw this on this side here, so this is A, this is B, right? So this is 10, 20, 50, and 40, right? So this path is would be in series and this path would be in series. So therefore, this would be what 10 plus 20 parallel to 50 plus 40 ohm. If you have confusion, you can verify this. I will be providing the materials. So this would be 1200. Not 1200, I'm sorry. It should be 120. 30 into 90 plus 30 plus 90. So 120. So this would be 4. 45 by 2 is 22.5. So therefore, this is your RTH. So similarly, I'll directly find out what is ISC. So this would be VTH by RTH, right? So this would be how much? 40 divided by 22.5. So this would be approximately coming out to be your how much? This would be approximately 1.78 amperes. So this is the answer. I hope this is clear. See, you can also find out ISC using, so you need to short these two terminals here, right? And then you can apply, KCL or KVL maybe. Not KCL, I prefer KVL to be better if you short these two terminals. And then you can find out what is the current in this path, the current in this path, and then accordingly find out the ISC, right? But I mean, you can verify that this would definitely be come out to be 1.78. That exercise you can do. Okay, so I hope this is clear, right? I hope this. If you have still doubt, you can ask. Hello, is this clear?
Yes, sir. Yes, no, sir.
Okay. Fine. So now let me just pull this thing a bit down and then again make space. Yeah, so this would be the last problem for KCL, sorry, for Norton's Thevenin theorem. So see here, I mean, we have solved plenty of problems for nodal analysis and also for KCL, KVL, right? I mean, Thevenin Norton, and there we also saw the dependent source circuits also. So you had a separate assignment on that, right? The assignment number I forgot, but you had a separate assignment on that. So if you can solve these kind of problems here, your analysis with dependent sources is completed. Okay, and the remaining is the two port theorem. So we'll see two problems on that, and another is that this mutual inductance ka problem. So that is very easy. You just need to remember the formula, that dot convention, right? If the two dots, if the inductor, the current through the inductor is entering the dots through the same side, then the mutual inductance would be positive or negative, right? That's it. I mean, the direction of the current through the mutual inductance would be negative, right? So that's it. So that is why I did not give any problem on that. So basically, you will get problems on KCL, KVL, then two port, then this Thevenin Norton, these dependent circuits, and some problems on uh, you know these things. So firstly, that AC analysis, so VRMS, that also we said that is also pretty easy, and secondly this uh, dot convention inductor circuits. So that's it, more or less. These are the heavy uh, things in network analysis. Okay, so now let us quickly go through this. So this is also pretty simple problem. I will try to complete this as quickly as possible. See here, they have told us to find out what is, I mean, there is a purpose of giving this problem. See, they have told us to find out the Norton's equivalent resistance and current. So for finding out the Norton current, we need to short this terminal here, right? So once you short this terminal, this is gone, right? This is equivalent to 0. Therefore, Vx would also be equal to 0, and therefore this is also gone, right? So therefore, what is your equivalent circuit remaining? This is what? This is 10 ampere, and this is connected to ground directly, right? And this is 6 ohm, and this is 10 ohm. This is your ISC. Now you know that the current takes the least resistive path always, so it won't flow to the left side. Therefore, directly you can write ISC is equal to 10. So in maybe in one step, your problem is solved. Okay. So is this clear? If is so, then I'll go
Yes,
to
sir.
the Thevenin. Okay, fine. Now let us just quickly solve this. So I'll just quickly apply a source transformation here. Right. So this would be how much? This is uh, 60 volts, and this is 6 ohm. This is 2 Vx. This is the resistance, right? And this is AB, right? This is 2. This is plus minus Vx. So let us say that this is the current that is flowing through. This is I. So VAB is nothing but 2 Vx, and Vx is 2I, right? So if I apply the this thing, so 60 minus 2 Vx is equal to 6 plus 2I, right? So again 2 Vx is 2I, so therefore this would be what, 4I, and this is 8I. Therefore I would be 60 by 12 ampere. So this would be 5 ampere. Therefore your Vx is 10 volts, which is equal to Vth. Sorry, not Vth. So Vth would be twice of that, right? Because Vth is 2 Vx. No, I'm sorry. No, Vth won't be 2 Vx. I'm sorry. Vth would be Vx only. Why would Vth be 2 Vx, right? So VAB or Vth would be equal to Vx only, because it is nothing but the voltage across this resistance. I'm sorry. So this would be only equal to your Vth. Therefore, RTh would be how much? It's Vth by ISC. This is 1 ohm, right? So this is the answer. I hope this is clear. Simple problem. Right?
Yes, sir.
Okay. So now we will. So these are the last two problems, and here we have a problem. This 20. This thing is pointing downwards. So just take I1 out of the picture first. Yeah. Okay. Okay. So now Let us look at the problem, last two problems, which is on two-port networks. This makes space. I think this much will do. Yeah. Okay. So here, see, for two-port theorems, I haven't, given any problem where you have a circuit, some resistance, combination of resistance, and from there you need to find out what is the Z parameter, Y parameter. No. So these kind of problems, are pretty favorite of the question setter. So you have this two-port network where you have this kind of either Z parameter or Y parameter or H parameter or ABCD parameter is given, and you somehow need to find out, let's say, what is the current flowing through 50 ohm resistance, or what is I1, or here in this case we need to find out the average power. So this kind of questions, one, you will definitely, I mean, I hope there would be one of these problems, because this type of problems were plenty of there in one of the assignment, probably assignment number 11, if I am not wrong. So the assignment was full of these questions, right? So that is why I have given both of these questions are in fact of this nature. Okay. And in two-port network, first of all, you need to remember what are the IV equations relating the the two ports of that network, right? That you need to remember. Okay. So see, this is a Z parameter. So once you note that, you quickly write out what is the equation. So V1 is Z11 I1 plus Z12 I2, right? So first, let me just quickly write what is the Z parameter equation, which is Z11, Z12, Z21, Z22, and this is, yeah, how much? This is 40, 20, 30, 10, and 30, right? So this would be how much? V1 would be 40 I1 plus 10 I2, and this would be V2 is equal to 20 I1 plus 30 I2. Right. So this is very important when you are finding out the, I mean, doing any two-port analysis ka problem. Okay. So now see here, this is given at an angle of, I mean, 100 at an angle of 0. So 100 at an angle of 0 is how much? This is polar form we saw. So this would be what? Cos 0 plus j sin 0, if you remember from our AC analysis. So j sin 0 is 0 and cos 0 is 1. Therefore, this is 100 volts, right? So we can write the equation at this part. This would be how much? 100 equal to 20 I1 plus V1, and similarly what would be V2 and I2? This would be minus 50 I2, right? Now we need to find out what is I2, and after that we can apply I square R, right? So why don't we write like this? So V1 would be 100 minus 20 I1, and V2 is this. So let us substitute V1 here. So V1, I am substituting 100 minus 20 I1 here, right? I am not writing any question number, I am directly writing. So 100 minus 20 I1 is equal to 40 I1 plus 10 I2, right? So this would be how much? 60 I1 plus 10 I2. This would be 10 equals to 6 I1 plus I2, right? And the other equation, so substituting minus 50 here, so this would be minus 50 I2, 20 I1 plus 30 I2, and this would be 80 I2, 20 I1. So I1 is nothing but minus 4 I2. So now quickly substituting this here. So substituting this I1 in here, right? So this would be how much? 10 equals to 6 into minus 4 I2 plus I1. Sorry, I2. So I2 would be, this is minus 24 plus 1. So this is minus 23, and this would be minus 10 by 23 ampere. Okay, so this is your I2, and finally the power that is dissipated in this 50 ohm resistor is how much? This is I square R, that is I square I2 square into 50, 10 by 23 square into 50 watts. So this is how much? Approximately this will come out to be 9.45. So this is the solution to the, see, this is a pretty simple problem provided you know how to, deal with the equations at this port and this port. So you will definitely get some problems where you don't know what is the circuit inside this two port network, but you know what are the relation equation, and I mean relating the two port parameter and the equation of the circuit outside this two port, right? And once you do that, you may be told to find out what is the open circuit voltage at at port 2, right? So in that case you need to open circuit 50 ohm. In that case I2 would be equal to 0. You put that in this equation, you will get some value of V2, right? So the process would be the same. So definitely you will expect some question of this type in the exam. Okay, so I hope this is clear. My suggestion would be that if you get this kind of
Yes,
problems, na, solve this kind of problems more, because this would be definitely there, this kind of problems. Okay, so okay, if this is clear, then we will go to the last problem.
yes, sir. Crystal clear, sir.
Okay, fine. This would be the last problem. So see here, here we need to find out what is the voltage gain. Now if you see VG here, VG is nothing but our input voltage, right, of this whole circuit, and V2 is the output voltage, right? So again, and this is our H parameter circuit. So once you are given the H parameter circuit, so you need to write the H parameter equation. What is our H parameter? It is nothing but V1 is H11 I1 plus H12 V2. Similarly, I2 is H21 I1 plus H22 V2. See, these equations you need to remember, and in two port you also need to remember what is a reciprocal circuit, what is a this thing, symmetric circuit, and also the equations of each of the the four parameters, right? We had discussed in one of the assignment, and I had also given a table, so you can refer to that. So these things you need to remember. Okay, anyways, so the parameters are given. So this is h11, this is h12, this is h21, this is h22, right? So now again, going by the same method. So what is VG? VG is I1 into 1K, right? That is ZG plus V1. Similarly, V2 is minus V2, I mean, sorry, 50K I2, right? So we need to find out what is the ratio between V2 and VG, right? So for that, what we will do, we will just straight away substitute this here. So VG is 1K I1 plus what is H11, it is 2K. This is also I1 plus H12 is minus 10 to the power 4, and this is a V2, right? Similarly, um, okay, so now let us just solve this. So this would be 3K I1 plus 10 to the power minus 4 V2. Now, what is I2 here? See, I2 is mm, H21 I1, right? H21 is 100 I1, and your H22 is 10 to the power minus 5 V2, right? But we also know what is your how I2 and V2 are related. So I2 from this would be how much? It would be V2, or yeah. So let us not write it like this. So let us do it like in this way. So let us substitute the value of V2 from this to this. So this would be I2 is 10 to the power minus 5 into minus 50 into 10 to the power 3, right? And this would be I2, right? So this would be I2 is equal to 100 I1 minus, this would be 10 to the power 4, so 0.5 basically, right? And this would be 1.5 I2 is 100 I1, right? I hope this calculation is okay. Just a minute. Yes. Okay. So now what we will do, we'll just
66.6.
no, we won't substitute I2 equals to something. We'll write in terms of I1. See, this is the catch. So I1 is I1 is this thing, right? So now what we will do, we will substitute I1 here. Okay. So Vg is 3 into 10 to the power 3 into 1.5 I2 plus 10 to the power 4 V2. I hope you understood what would be my next step. So this is gone. So 30 into 1.5 is 45 I2 V2. Right now we will just substitute this thing here. So I2 would be minus. So Vg would be minus 45 into V2 by 50k plus 10 to the power 4 V2. So this thing, right? So I'm just substituting I2 here. So if I had substituted I2 equals to, then there would have been no point, right? Because you see here we have got equation of Vg relating I1 and V2, and we have got another equation which is relating I2 and I1, and we have again got a equation which is relating V2 and I2. So why not substitute I1 in terms of I2 and then finally V2 in terms of I2? So if we do that, the equation becomes pretty simple. So here what this would be, if you do this, so this would be 9 into 10 to the power minus 4 V2, and this would be V2. So Vg would be 8 into 10 to the power minus 4 V2. So V2 by Vg, which is your gain, would be equal to minus 10 to the power 4. So this is minus 1000, right? So if we do this, this comes out to be minus 1250. This is your answer. I hope you understood what kind of analysis we did in this step, right? I hope you understood that.
Yes, sir.
So yeah, so if you do like this, you'll arrive at the answer. So these are, these are some of the good problems that I saw. Some of the problems are pretty lengthy, and some of the problems are pretty short, right? Especially some of the problems we saw here, right? Quickly we are able to solve, but in the exam, if you are confused, you will just apply KCL at this path. Then if you don't analyze a problem properly, it may go lengthy, and in that case, you will lose time, which is very valuable in the exam. So please practice the problems, and I urge that the problems that you got in the assignments, this assignment, and also we have seen the previous assignment, right? The assignment of the previous run, which we had solved till last week. You please go through that. Some of the problems, I hope there would be some problems in common and solve. So if you do that, you will get good marks in the exam. Okay. and this subject is pretty easy compared to other subjects in electrical engineering, and of course one of the most basic subjects. So uh, yeah, so with that we end this live session. I hope you don't have any doubt. If you have doubt, please do ask. We still have time. We'll
No doubt, sir.
okay, fine. So best of luck for your exam. I hope you will get good marks. I will upload these two things, so the live session recording and also the material by today night. Okay. Thank you. Good night and best of luck for your exam.
Good night, sir.